Hey everyone, and welcome to today's Explainer. We hear all the time about large language models getting wider, being trained on massive new datasets, or handling much longer context windows. But what about making them deeper? It turns out scaling depth has been a huge challenge. Today we're exploring a fascinating new research paper from ByteDance and Hwazong University of Science and Technology that tackles this exact problem with an architecture called Mixture of Depths Attention, or MODA for short.
Okay, let's dive into this. Here's our roadmap. We'll start with the information dilution problem, then meet mixture of depths attention, break down the read, operate, and write framework, see how they're making it hardware efficient, and wrap up with the real-world benchmark results.
All right, Section 1, the information dilution problem.
I want you to really think about this for a second. Why is it that when large language models get too deep, they actually start getting worse? In theory, deeper networks should mean more complex reasoning, right? They should be able to handle much richer hierarchical computations to solve harder problems. But in practice, modern transformers often just fail to turn those extra layers into actual benefits. Scaling width or adding data? That's straightforward. But scaling depth? That throws a massive wrench in the gears.
And here is why. It's a phenomenon called information dilution. Basically, as data passes through layer after layer of the neural network, the informative features that were formed early on in the shallow layers are gradually washed out. It's kind of like a giant game of telephone. The data gets subjected to repeated residual updates. Essentially, the model continuously overwrites and squishes the data as it moves forward. By the time you get to the really deep layers, those initial brilliant insights, they're completely muddled, totally unrecoverable.
Before today's paper, we basically had two flawed legacy architectures trying to solve this, and they were kind of like being stuck between a rock and a hard place. First, you have depth residual pathways. Now, these are highly efficient, but they suffer terribly from that information dilution we just talked about because everything just gets compressed. On the flip side, we have depth-dense networks. These perfectly preserve the history by connecting all the layers along the depth stream, but they demand computation that grows quadratically, meaning adding just a little more depth causes a massive explosion in required memory. The overhead is literally crushing at an LLM scale, so neither is a perfect solution.
Section 2. Meet mixture of depths attention.
So how do we fix this? Think of a standard transformer block as, well, actually scratch that. It's more like an assembly line. In MODA, they use this read, operate, and write conceptual framework. The read step adaptively gathers the current state alongside the historical depth keys and values from earlier layers. Then comes the operate step, where it uses attention to figure out exactly what historical information is actually useful for the current token. Finally, the write step takes the current layer's output and appends it back to the depth stream for the next layers down the line. It's retrieving data-dependent history without that crushing, dense, cross-layer memory overhead we just talked about.
But the true genius of MODA, the real game changer here, is the unified softmax breakthrough. MODA doesn't just bolt some clunky new depth reading mechanism onto the side of the model. Instead, it fuses standard sequence-level attention, which is looking at the words around a token, and historical depth-level attention, which is looking back in time at previous layers, into one seamless softmax operation. A softmax operation is basically just the mathematical function the model uses to decide how much importance or weight to give to different pieces of info. So the model is simultaneously weighing the importance of the surrounding sequence context and its own internal historical context. Absolutely crucial.
Moving right along to Section 3, making it hardware efficient.
You can have the most elegant, beautiful math in the world, but if it requires messy, non-contiguous memory access patterns, it's going to run terribly on a modern GPU. The authors knew this, so they engineered their way out of the memory bottleneck with a highly satisfying three-step checklist of GPU optimizations. First, a flash-compatible layout to reorganize the depth cache and turn irregular memory lookups into contiguous block reads. Second, a chunk-aware layout. And third, group-aware indexing. Let's dig into those last two.
Now, what's really interesting here is how chunking localizes the data. Instead of forcing every single query to scan the entire global depth axis, which, by the way, wastes massive amounts of memory bandwidth, the queries are divided up into chunks. Each chunk only accesses the corresponding depth span for its covered range. When you combine this with group-aware indexing, where adjacent query rows reuse the same depth blocks, your effective compute utilization just goes through the roof.
So, what does this all mean? How much of a difference does this engineering actually make? Try 1,458 times. Yeah, you heard that right. That is the shocking speedup this fused algorithm achieved over a naive PyTorch implementation. They took an incredibly slow, irregular memory access problem and transformed it into a massively parallel, tensor core-friendly operation.
All right, Section 4, Real-World Benchmark Results. Does this actually work?
Before we even look at the language scores, consider this single metric, 97.3%. The Moda hardware-aware kernel is so incredibly optimized that it reaches 97.3% of the efficiency of Flash Attention 2, and that's even at a massive 64K sequence length. To put that into perspective, that's equivalent to processing an entire short book at once. It definitively proves that depth-aware aggregating can absolutely be integrated without sacrificing our modern GPU efficiency.
And this brilliantly illustrates the actual impact. The authors trained models up to 1.5 billion parameters on 400 billion tokens. Across the board, you can clearly see the Medata architecture completely pulling ahead of a really strong baseline, which in this case is ALMO 2. Medata achieves lower validation loss and visibly beats the baseline on complex reasoning and reading comprehension benchmarks like Winogrand and ArcChallenge.
So let's summarize this victory lap. Across 10 distinct validation benchmarks, Moda improved average perplexity by 0.2, meaning the model is significantly less confused when predicting text. It boosted average downstream performance across 10 tasks by 2.11%. And the best part? It did all of this while incurring a tiny, virtually negligible 3.7% FLOPS computational overhead. Getting a massive performance boost across reasoning, common sense, and science tasks for just a 3.7% compute penalty, that is an absolute triumph for AI scaling.
If you really want to see the proof, we can look right inside the model's brain via its attention heat maps. When you look under the hood, you can see the sequence attention happening normally. But then across different heads and layers, there's this substantial, persistent attention mass lighting up for the depth information. The model isn't just looking around at its local sequence context. It's actively choosing to look back in time. It queries earlier layers to retrieve historical depth information to make better predictions. Seeing really is believing here.
By proving that explicit retrieval of historical depth information is practical, efficient, and highly effective, Moda has opened up a whole new dimension for scaling transformers. So, I'll leave you with this provocative thought. If information dilution is no longer an insurmountable bottleneck, just how incredibly deep will the next generation of large language models go? Thank you so much for learning with me today on this explainer, and I'll catch you on the next one.